Hi, my name is Levi. I'm an astrophysics major here at MSU, and this is my presentation for CMSE 201. I decided I was going to try and classify stars found by the Gaia mission. I started with a broad question. I just wanted to look at the classifications of stars, or even star clusters, found by Gaia, but I quickly discovered that wouldn't work with the dataset that I had gotten from Gaia. I'll have to explain a bit about astrophysics on the next slide, but all you need to know about Gaia itself to understand this presentation is that it is a space telescope that created a 3D map of our galaxy. And here you are looking at the flattened 3D map of all the stars surveyed by the Gaia mission. My dataset ended up having 253,040 stars in it. The blank spot on the graph is where the cameras couldn't reach on the spacecraft. So imagine you have a 360 camera, but you can't take images of where the camera actually is. That's where this blank spot is. You'll see on the graph that the stars are plotted based on their right ascension and declination, which are basically the latitude and longitude on this thing called the celestial sphere. You can see an image of this on the right, and it's kind of hard to understand, but what helped me is imagine that you're in a bubble and you label everything in the room around you as a coordinate on the bubble instead of an actual physical coordinate in the plane of the room. Right ascension is usually measured in hours to go with the rotation of the Earth. However, this dataset had it in degrees, and I decided to keep it in degrees to make it less confusing for anybody who's not an astronomer in this class. As I mentioned before, this was too much data to pull anything from, so I tried making a random cut and still got nothing. So I decided to change my research question. I looked at sun-like stars because classifying stars that are similar to the sun allows us to view exoplanet transits. Exoplanets being planets outside of our solar system, and transit meaning when the planet goes in between us and the sun that it's orbiting so we can see it. And this allows us to look for planets and planetary systems like our own in order to better understand ours, how ours formed, and where ours is going. Additionally, prioritizing travel to these systems is crucial if we want to learn more about our own solar system or even our own planet. I'll go over my diagram in a moment, but please turn your attention to the one in the top left. This diagram is called a Hertzsprung-Russell or HR diagram. It displays a striking correlation between luminosity, or the brightness, also known as magnitude of a star, and the temperature, which also directly correlates to the color of a star. Stars which fall along this correlation are called main sequence stars. Outliers, such as giants and white dwarfs, are easily identifiable on this diagram, as seen in the example image made by Nick Strobel. Please note that HR diagrams, or CMDs, which are the simplified version that I made, color magnitude diagram, are not the only way to look at correlations between stars. In fact, astronomers tend to take many different variables and compare them. I started by selecting two stars that were physically near each other, but also near our sun on a CMD. Then, I selected the star with properties most like our sun because it would be the most valuable when considering space travel and even when doing research. When adding the rest of the stars from my dataset back into my graph, I found that the sun-like stars appear to be outliers. I know that Earth is a rare planet size, as the most common size that we know of are called super-Earths, so I can only assume that something similar is happening here, only it would be the opposite. While our star is a main sequence star, it is small, and this explains why it has a lower magnitude than the other stars found by Gaia. However, it could also be a data bias, because magnitude is a relative measurement, and I don't believe that Gaia surveyed the sun. So all of the other stars are measured relative to each other, but I had to use the absolute magnitude of the sun, which is the magnitude measured at a specific distance. While traveling to this star may be valuable depending on whatever planets may or may not orbit it, the fastest spacecraft to date is the Parker Solar Probe, traveling at 466,592 kilometers per hour at its max speed. I won't bore you with the calculations, but traveling at that speed with this particular star in our sights would take 11,023,192 hours. So, it's not possible today. Please ask questions below, and if you'd like more specific clarification about any of the astrophysics topics I didn't go into details on in this presentation, feel free to contact me. I decided to change my research question. Why is this worded so terribly? Why? Why right now? Why? I hate my neighbors. I'm closing my window.